Good morning or good afternoon, depending on where you are at. My name is Atarot Azizi Namini, Director of the ABC UTC at Florida International University. We have some really exciting news that we would like to share with you about our conference. Two deadlines that you need to remember is one is the deadline to submit the abstract, which is August 27th, and October 8th to submit the nomination for award. Again, these abstracts should be based on the knowledge that is produced outside the US. The focus of the 2021 conference that will be held in December 8 to 10 of 2021 is on the international experience. 2022 will be very similar to our past conferences. 2021 conference is going to be completely 100% virtual, December 8 to 21. 30 state DOT, FHWA, TRB are co-sponsor, including the IAPC. And we have some list of keynote talk and keynote speakers that we would like to introduce to you. The conference will kick off by the few comments by Carmen Swanwick, the chair of the AASHTO COBS. Our keynote speaker will be Dr. Firas Ibrahim, that I call a man of ideas with the US DOT, so we are very delighted to have him as a keynote speaker. We have assembled some really impressive list of international speakers that I'm sure that you're going to enjoy the presentation. From Switzerland, we're going to have Eugene Bruweiler that's going to discuss the bridge deck overlays and beyond. From Sweden, we're going to have Dr. Peter Collin, that's going to discuss some innovative prefabricated system that they're using in the Europe. From Switzerland again, we're going to have some examples of the UHPC field applications. From China, Dr. Xu is going to be discussing the ABC and the high-speed rail. From Berlin, Germany, we have a very interesting presentation by Mark Shelley that's going to discuss about the ABC and the role of the prefabrication in bridge construction. Dr. Zhao from China is going to be discussing how the ABC and the prefabricated bridges are being used in China. And everything is being transformed in a digital form. So we have two very knowledgeable speakers, McDonald from London and Joseph from Amsterdam. This is going to discuss the digital transformation and building a smart. So this is a really interesting one that is going to introduce you to some of the effort that's going on with digitizations. On the US side, we have some invited keynote speakers that are very familiar with you. That's why we didn't put the names: Ben Graybill, Bala, Mike, Kulmo, Wasim, Ted Zoli, and Doreen. So everyone in the bridge community knows them. The conference is also going to include the awards program. So we're going to give awards, and the award committee is that you see the members here, and it's going to be chaired by the Ahmad Abu Hash. How do you submit your abstract and the nomination for award? Please go to our website and you will see all the list.
Our webinar today features Nebraska's recently fully precast Belden to Laurel bridge replacement project. We're pleased to welcome our presenter, Mark Traynowicz, State Bridge Engineer with the Nebraska Department of Transportation. Mark?
Thanks, Mary Lou. And thanks for having me today. I'm excited to share this project. We had a great project, and we've done some interesting things in Nebraska. We haven't done a ton of ABC, but we've done some really interesting things I think you'll all enjoy. So sit back and enjoy some of my photos as we go through this. Okay, so going to talk about our Belden to Laurel project. But before that, I'm going to talk a little bit about just a brief history of our accelerated bridge construction in Nebraska and really how we got to where we are. Then I'll talk about the Belden to Laurel project, about a brief precast bridge project, then a little bit about where we're going, and then I'll wrap up with a really exciting workshop that we're having September 30th in Omaha. So here we go. So where is Nebraska? I guess where in the world is Nebraska? Here it's shown in the middle of the United States, and of course, it's got to be shown as Husker red. So if you didn't know where Nebraska was before this, now you do. So history of ABC in Nebraska, and really how did we get here? We went through a few projects dealing with precast deck panels. We did some steel tub girders, and we've evolved through that, of course, and we've got to the precast elements, and then some precast approach slabs that we're finding are working for us pretty well. So back in 2002 was really our first, I guess what I'd call an accelerated bridge construction project. It was on a bridge just west of Omaha. Probably not the easiest bridge to start with, uneven spans. We had a 25-degree skew. It was a crowned roadway, so we're putting deck panels on a crowned roadway. And we tried something new with the 1 1/4 diameter steel stud shear connector. I won't talk a lot about that, but it comes into play later. So this is the project, and you can see on the left, we set the panels, they're full width. It was a crowned roadway, so we actually had the panels, we had a hinge, if you will, in the middle to make the crown go both ways to basically break the slope to go both directions. The open trough, the post-tensioning strands went through the open trough. They were mid-depth of the precast panels, and we'll talk a little bit more about that later as we go on. And then after this one, of course, we had to finish this with an overlay. We put a concrete overlay on this on these panels on this bridge when it was finished. 2003, we did a project using steel tubs girders, a little more simple project, equal spans, 0 skew. We did use 100 KSI high performance weathering steel. We believe it was the first bridge with 100 KSI high performance weathering steel in the United States. So we got that feather in our cap. It was really simple. The contractor really felt it was simple to erect these girders. Again, it's kind of going towards accelerated construction. I'll show you why in a little bit. But we literally we shut the interstate down for a night, put the girders up, and then open the interstate back up after that. You can see the finished bridge on the right side. We went on in 2008. We did another project with steel tubs. This time we did have a skew, made it a little more complicated, a 24-degree skew. This time we used 70 KSI high performance weathering steel for the steel boxes. And so this will get a little bit more into, or a lot more into accelerated bridge construction. You can see we actually we pre-topped or put the deck on these girders. They were at the site. They weren't on the substructure, but they're off to the side. The contractor placed the deck on. You can see on the right side these headed rebars. So this was before we had used ultra high performance concrete, so we didn't do that here. We just used regular concrete, but we used these headed rebar. These were screwed on. The rebar was threaded, and these heads actually screwed on like a nut. It took a lot of time to do that, and they're expensive. I think they were $1 or $2 per head, and that was back in a number of years ago. So just showing the progression of where we've gone to. Pretty easy, pretty simple. It took an overnight closure. Contractor Hawkins lifted these into place, the 3 segments, and basically in the morning you pretty much had a bridge in place. So 2 span, so it took 2 nights of closure, but process went really, really well. Dr. Aziz Yamini was in Nebraska at the time and helped us out with this project. On to Primrose East. This was folded plate girders. This was looks like a very simple bridge, but there's a lot going on with this bridge. We did this in 2014, just a little simple span 50-foot bridge, 0 skew, so that helped. But we had steel folded plate girders, again through Dr. Aziz Amini. We did a geosynthetic reinforced soil abutment. So that made the abutments pretty simple. We had precast elements, and this was our first effort into ultra high performance concrete. So the folded plates were delivered near the site. It was basically in this little town of Primrose, and the bridge was a mile or two out of town. So we set this up, contractor set this up and pre-topped these girders with the concrete deck off-site, brought them on site. You can see it on this right picture where they had lifted them into place. The deck is on, the back wall is on, and they just put these side by side until they basically had a bridge. So here's the difference between the other bridge I showed you, the 262nd, that had the headed rebars and the wider opening. On the left is the joint between the deck panels, or the deck segments, and we use ultra high performance concrete for this, so that the spacing is much more narrow. It's just a straight bar with no head on it. So it was really very, very simple to do. Of course, we had to get the contractor in, the supplier to come in with the ultra high performance concrete and to do that work. But it really, it was interesting. It worked well. We actually did a water test on this to make sure the joints weren't leaking, and it still is just a really tight structure, and we're really happy with this project. Our last one I'm going to talk about before I get to our topic of the day is our Kearney East bypass precast deck panels. These were full depth this time. Okay, this was done in 2016. Equal spans, but we had a 14-degree skew, so it makes it a little more complicated. They were twin structures. One was cast in place concrete deck, and this one was precast deck. It was a tangent roadway, so we didn't have to deal with the crown, and it was over both a railroad and a highway. So you can see I'm lifting the panel on the left side. It's full width. So again, it was a tangent roadway, so the slope went from the median all the way out, so it didn't break like a crowned roadway. So this one was easier in that respect. This project, we actually did the post tensioning underneath the panels on the Skyline project with the open troughs. The post tensioning was mid depth of the panels. This was underneath the panels. Of course, we were a little concerned by doing that, but with going through our University of Nebraska and doing some research with Dr. Mayor Tadros and Dr. George Morkos, we really found we could do this, and it worked out really, really well. On the left, you can see what the panels, this is when they're set, but there's no overlay. We've got little vents in there, so when we pour the self-consolidating concrete on top of the girders and underneath the panels, these are little vents where the concrete will come up. I'll show you more on that on the Belden project. And on the right is the single strand post-tensioning. So really, this was a very simple project. It turned out really, really well. But with anything, we always want to make improvements and get a little bit more innovative. So that brings us to our Belden to Laurel, our All-Precast bridge project. So I showed you where Nebraska is. So if you look down, this star at the bottom is Lincoln. If you can see my cursor, up here towards the top is Norfolk. That's where our district people are. And just a little bit north and east of that is where this project is located. About 140 miles from Lincoln to the project site. Lincoln is not only where our bridge design team is at, but it's also where all the precast elements were fabricated. And there you can see the site. Again, 140 miles from Lincoln. There you can see about the site where we were in reference to where our offices are in Nebraska. So a lot of thank yous to folks that did this work. Concrete Industries did all the pre-stressing and the precasting. They're right here in Lincoln. They have done a lot of work for us with our NU girders and our IT girders, all of our precast concrete type structures and girders. Simon Contractor out of North Platte did the work, had really good communications with Simon during the whole project, not only with Simon, but with our district people up in District 3 in Northeast Nebraska. So that was, the communication was key. Of course, University of Nebraska, we couldn't have done this without all their help with their research efforts. And of course, our partners at Federal Highway Administration, Ben Graybill with Ultra High Performance Concrete, and David Mraz, our division bridge engineer, were really instrumental in helping us with this project. So the existing structure, just a 100-foot 3-span steel girder bridge, was built in 1938. It carried Highway US 20, had a average daily traffic of about 2,000 vehicles per day and about 25% heavy trucks. This project also had quite a scour problem. The stream had degraded over time, and so we had some, we tried to correct some scour issues a few years before this, and it just didn't work. Had some more high water, and so it was really, we had some scour concerns with this existing structure. So we decided to do a precast element bridge, do it quickly, do it accelerated. So the bridge that we determined, we went to from a 100-foot bridge to a 130-foot bridge for the new bridge, 43-foot wide, 10 degree skew, so just enough skew to make it difficult. Of course, it's always better when it's square, but I guess I want to tell everybody you can deal with skews. You don't have to find a square bridge to do accelerated bridge construction. We've done plenty of what we've done with skews. This was constructed in the 2018 construction season, designed by our in-house NDOT staff. Steve Sabra was our lead bridge engineer and just really did a great job with this project. Design, bid, build, so it was let to contract. When the bridge was closed, there was a 13-mile detour for the traffic that needed to get around this bridge. We gave the contractor 45 calendar days to complete a road closure to complete the project, and about a $3,800 or $3,750 per day incentive or disincentive if they either got the work done earlier or got it done late. And the incentive was capped at a 10-day maximum. So the objectives of the project, we really, of course, with ABC, you want to minimize road closure. And really what that means, we're trying to maximize safety. So, get in, get out, and stay out, get traffic back on top of the road. We wanted to expand on our NU precast pre-stressed deck panels. We simplified the deck to girder connections. We provided a non-post tension option using ultra high performance concrete. We added the precast rails to the precast deck panels, which really was a good deal for us, I think. And then we basically utilized the whole substructures of precast: the abutment, caps, back walls, wing walls, grade beams, and approach slabs. So the precast element fabrication, here's all the pieces. I won't read through all of them, but all the way from the girders to the paving sections, 55 pieces. These were done at Concrete Industries in Lincoln, Nebraska, and then shipped 140 miles from the fabrication site to the project site. So basically we took 55 pieces, these Lego pieces, if you will, built them in Lincoln, shipped them to the project, put them together, and used some concrete to hold them all together. So we did have some, of course, had some field cast concrete to connect the precast elements. The types of concrete we used, we had high early strength concrete, which was 3,500 PSI in 48 hours. That's in the picture to the right. That was the one joint that we used, or one of the joints we used a high early strength concrete in. Self-consolidating concrete that would flow underneath the panels, deck panels, and on top of the girders. That would reach, required to reach 5,000 PSI in 28 days. And then of course we had the ultra high performance concrete, which, these numbers blow you away, but 12,000 PSI in 4 days and 21,000 PSI in 28 days. We limited that use to mainly the transverse joints on the deck panels and the joints on the bridge rails. So the precast element fabrication at Concrete Industries started in April 9th. It was completed May 23rd. And this picture here shows the abutment caps Now, interesting thing about this picture, the abutment caps, when they cast them, they were cast on their side, and I wondered why that was. But as I looked into it more, Concrete Industries uses almost exclusively self-consolidating concrete. So the top of the abutment cap was stepped down because of the slope of the roadway. So in order to have the self-consolidating concrete work, they had to pour it in basically they had to make the side the top because that was a flat surface. So on the left are the precast deck panels, precast pre-stressed deck panels. If you look closely, you can see the pairs of pre-stressing strand. So they were pre-stressed transversely. One other thing, of course, there's a cross slope on the roadway of 2%. So the bridge rail had to be tipped in, if you will, 2%, because they also, once they were set on the bridge, they had to be plumb. So a little bit of attention to detail when it came to the bridge rail. On the right are the shear connector pockets, which was a simplified version for this bridge. We made them round this time. In the past, we had either had the open trough like you saw earlier, or it was a square pan. And there's a hole in the middle, and you'll see a little bit more later, but if you see the hole out here in the panel, it's a vent hole for when we pour the self-consolidating concrete on top of the girders, and it vents out, so we know that the concrete has gotten to that point. So here's some of the deck panels that are finished in the yard. A few of the 55 pieces that are waiting to be transported up to the project site. If you look down here to the bottom right, so if you see down here, this is the transverse joint. These are 6 inches of rebar sticking out. Here's the bottom lip we use to help form for the ultra high performance concrete. But all this has been sandblasted to roughen the surface, so the ultra high performance concrete actually adheres better. One of the one of the lessons learned, if you look here in the middle, this would form a transverse joint. These rebar actually stuck out further than the bottom lip. So when you set this panel, you couldn't just set it straight down, because you'd break off the lip on the other side. Or if this panel were set and this panel came on top, it would catch this rebar. And you also had these other rebar that had to miss some of the shear connectors on the middle girder. So I'll show you a picture of that later, but that was one of the lessons learned as we went through this. So our NU girders, these were NU 131 foot NU 1100 pre-stressed girders. Of course, the fabricator used self-consolidating concrete. So with the concrete strength of 8,500 PSI at release and 10,000 PSI at 28-day strength. Pretty high, we try not to go that high, but we definitely can if we need to, and Concrete Industries did a really good job for us. The shear connectors are different than we typically use. These were actually 1.5 inch diameter threaded rods at 4 foot spacing. This was something that we had worked through AASHTO and T10 on one of our previous projects to work to make sure these types of shear connectors were going to be acceptable. And these are the shear connectors that sit in those shear pockets, those round shear pockets that I was talking about earlier. So construction. Contractor closed the road, Highway 20, on May 29th to start work. It took them 4 days to remove the existing bridge and prepare the structure for the new bridge. We drove pipe piling, and it took the contractor 12 days to drive 46 pipe pile. The pipe pile were lengths of 80 feet for the abutments, 40 feet for the wings, and 60 feet for the grade beam, or where the approach slab sits, or approach span sits. One thing that they had to make sure of course, these pile need to fit inside a precast cap or wing, so they need to be pretty exact. So it took a little bit more time to make sure that they were driven in the right place. So once the concrete pieces, once the precast pieces got there, they all fit together. Of course, nothing goes completely as planned. This is one of the washouts. This is the contractor crossing to get from one side of the creek to the other. You can see the bridge up here on the upper left. This happened 4 times during construction, so it was an active channel, a little bit too active for our project or for our likes. Again, probably one of the reasons why we have some string degradation and scour through here, but one of the things that one of the unforeseen risks that happen, and we just have to deal with. So the pieces were pretty big. So the contractor needed to rent a 200-ton crane to lift the heavy pieces. This upper right, this was shown on the front sheet of the plans. So the girder weight themselves was about 48 tons. The abutment cap was the big piece at 58 tons for the abutment cap, including the back wall. Now, we did give the contractor the option to have that come in 2 pieces, which they chose to do, and I'll show you later. So the abutment cap was about 48 tons and the back wall was about 10 tons. So they broke it up so it was a little bit more manageable. The other big piece, of course, were the grade beam at about 32 tons, and these paving sections got to be pretty big too. These basically they're basically sitting on grade, so they're just a big slab of concrete that sits on the subgrade. So the abutment caps were set on June 12th. You can see them being pulled off the truck, lifted off the truck here, and moved into place. The contractor had to do some. They used some supports. The pipe piler underneath. They used some supports to hold the concrete on top of the piling themselves. So this was one of the largest piece, and you can see it here going in a little bit better over here. You can see on the right, you can see the pipe pile sticking out and how they had to line it up, and then it's sitting in place on the left. So looks simple. It gets less simple with the weight and trying to line up the pile around those sleeves. Took 3 days to place the rebar in those pockets and fill the pockets with highly strength concrete. Also had to drill and set some anchor bolts in the field. One of the lessons learned that we had the pipe sleeve, the CMP sleeve that was cast in the precast element. It had to fit. The pipe pile had to fit inside of that, and then this rebar had to fit between the sleeve and the pipe in the pipe pile. So we'd probably, if we did this again, or when we do this again, would make probably little less penetration of the pile into the substructure, and potentially make the pipe sleeves a little bit wider or a little bit bigger, just so everything fits together better. Girder erection only took 2 days. You can see them set here again, 131-foot girders sitting on the sole plates. Pretty basic right there for us with these NU girders. One thing that was a little unexpected was we anticipated 8.5 inches of camber. These girders actually grew to 11 inches. As you can see here, they just, they bend up quite a bit. So we had to modify, the shim, the distance between the, top of the girder and the bottom of the deck panels. Of course, that had to change the grade a little bit. So we had to modify things a little bit, but it didn't slow us down too much. This shows the girders as erected, and so that you can see the threaded rods on the 3 outside girders on each side. These are where the deck panels will sit. The middle is left open, and so the shear connector is a little bit different, or a little bit more normal, not quite, but a little bit more normal than what we typically do with shear connectors on our typical girders. The abutment back walls only took 1 day to set. So what we had originally, we had the abutment cap, which you saw get it placed earlier, and the back wall all together as one piece. We made it an alternate design where they could do them separately, and it worked out better for the contractor and the fabricator to do them separately and just connect them in the field. The wings and grade beam took 4 days to prepare and set. It took some digging. It also, because the wings weren't symmetrical, just to pick them up and pick them up straight and level took a little bit more. It was a little bit more of a challenge, and to get them around the pipe pile, get the sleeves around the pipe pile, took a little bit more effort than we originally anticipated. I think you can see it better on this slide. You can see where you've got the wing wall, you've got the sleeve, and then you've got this block around the sleeves. So if they would just pick it up straight, of course it would tip in, and in order to make it pick up level and plumb, they had to rig up the pick a little bit different. The grade beam that will go back here, I don't think I have a picture of that, was probably the most simple piece to put in, and so that one worked out very, very well. It took 8 days to drive the sheet pile. So the sheet pile are needed, as I talked about earlier, the bridge that was there had some scour concerns. It had some stream degradation. You know, we're putting these bridges in for 75 or 100 years, so we know the stream is going to change at some point in time. So we put these 33-foot long sheet pile, they're basically cold formed sheet pile in, and you know, just the length of them was difficult, but it was something that we needed just to make sure for the longevity of this bridge. So that took a little bit longer than expected, but we got through that. And you can see the sheet pile go, these of course are the girders, this is the abutment back wall, the sheets go behind there, just to keep the fill retained if the channel itself were to lower. And there, we also have them along the inside of the wing. So here's the wing wall, and then this is the grade beam that I talked about earlier, where the approach span will sit. So the deck panels showed up on June 28th. So we began setting the deck panels. You can see the roughened surface. You know, these are the transverse joints. These are the joints on the bridge rail where the ultra high performance concrete will be placed. This is setting the first panel. You can see they did some styrofoam blocking or formwork, if you will. And I think I have a better picture of this next one. So you can see the styrofoam side forms for the self-consolidating concrete. And then if you see these little shim packs, that's how they set the grade for the deck itself. And so what happens is this void in here will eventually be filled with self-consolidating concrete to support the deck panels on top of the girders. And here's the shim packs that you can see again here's the girder. Okay, they're sitting on top of the girder. This is the pack to set the grade. You know, this would be the grade where traffic would drive. Here's that form. So these are the transverse joints, and you can see they go together. So you really just have to put a backer rod in here basically to hold the ultra high performance concrete. These 6-inch bars actually stuck out farther than this concrete lip. So if you were to drop this straight in, this one would hit that bar. So you had to kind of bend them in. Unfortunately, you also had these bars that went across the middle girder, and there were some shear connectors out here. So it was a little bit of a challenge to get those in without breaking that lip off. So here's a little better side view. So the panels they're only half width. Okay, again, this is it's a crown deck. Okay, so the panels were half width. This was actually high early strength concrete was placed here at the end. The great thing about doing it this way is number one, the panels were lighter. You know, we had never done bridge rail attached before, so it was a little bit easier to set these. That way you could really, you'd reference your panels off the front face of the rail. Okay, so the next panel that got put on, you'd make sure the rail lined up. And then you could, any difference, any tolerances could be taken up here where we cast the high early strength concrete. This shows the underside of the panels. These are those pockets galvanized. And so other than that, there's nothing else down here. So that, you know, basically the girder sits under this way and under this way. So as the self-consolidating concrete is cast or actually poured through this hole, it actually flows to the next one up, and then the air comes out till it's full, and it just keeps going that way. So it's something that we did on our Kearney project, the one I showed earlier, but that one they had square pockets and this has round pockets. We think this worked quite a bit better. Just shows the deck panels being set. This, of course, is the middle girder where we cast high early strength concrete. This is where we'd put the self-consolidating concrete. So each one of these shear studs would come up through the pocket. It wouldn't come through the deck. It would just sit in the pocket. It would have to, the shear stud would have to actually be above the bottom of the panel, but of course below the bottom of the deck. And what we've done a research project to, because sometimes it's pretty hard to line these up, right, to get them to fit inside that pocket. So we've got a research project that's completed by Dr. Morkos about having just regular shear connectors, a little bit different than this, but not really changing what we do with our girders. So the shear connectors are actually below the panels, so we don't have to worry about them getting up above the bottom of the panel and making them fit, and using ultra high performance concrete to fill up those, to fill up the void. So again, another advancement with our university. Last panel was set July 13th. So the panel themselves took 4 days for the contractor to set. Of course, there was other work going on at the time. They were putting the wings on, they were putting the grade beam on. So a lot of concurrent things happening, but only 4 days for setting the panels. Again, you can see the pockets, and you can see the, this is actually the end panel that'll hook onto the approach slab. So we're preparing the deck now to do the cast in place concrete. We've got, you can see that the first thing that was cast would be the high early strength concrete over the middle girder, then would pour the self-consolidating on top of the girder, but underneath the panels, which would go this way. And then finally, we put the ultra high performance concrete in the transverse joints. So a lot going on in this picture, and you can see the shear connectors on the middle girder right there. Just another view of it. You can see better, the void underneath the girder where the self-consolidating concrete will flow, and the high early strength here. And of course the back wall and where the approach slab will sit. So here's what it looks like. This is where the self-consolidating concrete goes. It comes down through one of the vent holes, the grouting hole, fills up, flows on top of the girder, and it just moves right down to the next hole, comes out the next hole, you cover that up, and it just keeps on going. So the improvements that we wanted to make, and I think we did make on this one for our deck panels, we included the bridge rail, which I think was a big thing. We simplified the shear pockets, which was helpful. And instead of using post-tensioning, we used ultra high performance concrete. So we just took another step out of the process. This shows getting ready for the self-consolidating concrete. I'll show you a different picture of this in a minute. But so you'd pour down through one of these vent holes, it would come up through the next vent hole. Once enough came up, you'd slide a bucket over top of that to hold it in. It would go to the next vent hole, slide the bucket, and so forth. I think they could probably go more than a panel, but they kept it about maybe a panel or a panel and a half before they would use or would move the this contraption, I guess I'd call it, to place the self-consolidating concrete. So here's Dr. Marcos, who helped us with research, standing out there while they're doing the self-consolidating concrete. You can see that the aggregate, really the spread and the aggregate and how it's just so uniform throughout. We've been doing self-consolidating concrete in Nebraska for a long, long time. And it just has been working out great. At one time it was only in the plant, but now we're getting much better about doing this in the field. Here's that placement contraption, if you will. So you're pumping the self-consolidating concrete is going down this funnel and into one of these holes, and then it'll come up through these next holes, if you can see that. So here's the I guess the order. So first thing was fill the big joint in the middle with high early strength concrete. You fill self-consolidating concrete over the girders, and then after that you do the transverse joints with ultra high performance concrete. So we tried to do all the ultra high performance concrete at one time, including the bridge rail. So you wonder about, okay, you're pouring that self-consolidating concrete and you're doing it blind. What does it look like? On the right, these are those styrofoam forms that I showed you. On the left, we actually took the styrofoam forms off of places, and you can see it really conformed. It looks just like the styrofoam. That self-consolidating concrete does such a good job. And as you can see, our girders are all self-consolidating concrete, and it just makes a really smooth, conforms to the form really, really well. Placing ultra high performance concrete, we've got our chimneys, we've got our transverse joints, we've got our covers. And so that's the setup to do it. You can see the bridge rail forms on the bridge rails. There's a close-up view. Same kind of joint, 6 inches, formed it up and poured the ultra high performance concrete inside. Same type of spread, but of course this has the steel fibers in there that give it the strength. Very flowable material. We placed these boards here because we place it a little bit high and then grind it off. That's why these boards are here, and also to hold down the cover cap as it moves from across the bridge. Because with the cross slope, if you just left it the way it was, it would all flow to the bottom and not cover the top. So you have to, at least we had to cover it. Precast approach panels. So you can't have an innovative accelerated bridge construction project in Nebraska without Fuad Jabber being a part of the picture. Fuad's been really instrumental in all of our innovative things that we're doing in Nebraska. Many of you know Fuad, and here he is out on the project checking out one of our approach panels. This is placement. Really special thanks to our District 3 construction people. Tony Vogel was the project manager up there and did a really great job. Just understanding how this all went together. Rob Davis, the assistant construction engineer up there, they just understood that communication was good, and it really, really went well. Had a good contractor, had a good construction inspection team, went really, really well. So we were really happy about that. Just the placement of the approach sections. We had we did the ultra high performance concrete with the rest of the bridge. We filled the pockets at the grade beam and then did the longitudinal joints with high early strength. Here's the last paving section panel that was set. The crew that did it, good group of people, did a lot of great work for us. It's hard when you do this. It's hard. These guys are working long hours. They're pushed by this time constraint. Get stressful at times, but Simon Construction really, really did a nice job, and it's good to see. Good to see most of these guys smiling at the end of the project. And the completed project opened to traffic July 26th. We put a waterproofing membrane and an asphalt overlay on top of the bridge just to preserve that and make it congruent with the rest of the roadway. A few observations and lessons learned. Of course, support from our administration, super important. Input and communication with the contractor before, during, and after is really, really important. Our precast elements, shorten on-site construction time, minimize traffic, improve safety. One thing is really imperative, I think, durable joints. Durable joints, you need to have a durable joint to make this a long-lasting bridge. The precast elements themselves will last a long time because they're built in a confined area, in an area where you can really take care of things. Oops, did I just lose? Can you still hear me? I think I just lost connection.
We can hear you. We can hear you.
Okay, good. I heard something crackle. Last couple of slides. We did have 4 contractors bid on this project. It was mostly an asphalt paving project, but it had an ABC bridge within the project, but we had 4 contractors bid. Of course, we talked about the blockouts for the piling. We'd probably make those bigger next time. Contractors, of course, we all have a hard time keeping workers, but ones that are willing to put in the extra time and stress when it comes to the long hours and the extra commitment with an ABC project, that's always a concern. And with all these pieces, you got 55 pieces, and sometimes the contractor felt they didn't have enough space, enough right-of-way for all the pieces and equipment to get this thing put together. So right-of-way concerns are always an issue, and if we can make that as much room as possible, the better off we are. Communication is always key. It went great on this project between our district people and our fabrication people in Lincoln and our bridge design people, and the contractor was really good. We've got a great relationship with our local AGC here in Nebraska. And research, we've just done some really good things along with this project. I did talk about this precast concrete deck to girder connection using ultra high performance concrete. This was done in 2019. That's where we didn't have to get the shear connectors up into the deck. And then we're also currently doing an accelerated bridge construction decision tool. Both of these professors will be attending the September 7th training from Connecticut. So Mary Lou, plugging that for you again. I think it's important for all of us to have these types of tools. And I think that training on September 7th with FIU is going to be a really, really good thing. Where do we go next? I've got 2 more slides. We're really excited. We've got ultra high performance concrete decked NU precast girder that we're in the midst of a research project now. We've got a couple of sites we think we have picked out to build these things, and we really feel like this is part of the future, if not the future. To build something like this, it's going to last a long time, and just serve the traveling public for a long time. We're really excited about this project. That's all I have for my presentation. I appreciate your time and patience.
All right. Thank you, Mark. Thank you, Mark. I always say good ideas comes from Nebraska in bridge engineering. So with that, let me turn it to Paul Lyles and Romeo Garcia, who are going to be moderating the question and answer period. We did get tons of questions. So Paul, it's all yours.
Okay, Mark, thank you. And thank you, Ettore. Mark, really interesting. And we've got a bunch of questions that have come in during the presentation. So certainly as many as we had beforehand. Let's go, first of all, we've broken the questions down to maybe design and construction questions, and maybe some cost questions, and then maybe some general questions. But with that, let's go ahead and get into it. First question I have, and these came in beforehand, it says, what was the accommodation of the precast deck, bridge deck cross section for crowning? I think you showed that, but you just might.
Yeah, I think I covered that. This project itself, they came in 2 pieces from the side, so we took care of the crown that way. The first project we did, we actually put a hinge in it, so we broke the crown that way. And on their other one, it was a tangent roadway, so we didn't have a crown. So if I guess for precast panels, if you have twin structures, it makes it a little bit easier.
Okay. Here's a question that came in: was lightweight concrete considered for any precast elements? And would it help to reduce piece weights for hauling and erection?
It would help. Of course, it would help to reduce weights. We didn't consider it. I think it's something that could be considered, should be considered in the future. I guess you just you weigh that the cost of regular weight concrete as opposed to lightweight concrete, but it definitely should be looked at.
Okay. Here's another question that came in earlier. Did you have any difficulties finding a source for UHBC for the closure pores?
You know, we really didn't. You know, it was a proprietary blend that came in. The folks from Lafarge came in to do the work. We've developed an ultra high performance concrete through the University of Nebraska and through Dr. Marcos. So we do have something that we're looking to use now that's non-proprietary. I think a number of states are doing that. You know, frankly, ultra high performance concrete is becoming a lot more mainstream, and there's other places to get it these days.
Okay. These are some questions that came in during the presentation. I'm going to ask some substructure questions first. The first one is, can you explain more about the piles under the grade beam under the approach slab?
Sure. So what we do in Nebraska, so at the end of our bridge, we have an approach section, okay? And it really acts, so from our abutment to where the approach section spans, we put another cap, if you will. So it's really a bent cap, if you will. And so it spans from the abutment to the grade beam. So it's supported on those two supports. And then we have another piece that goes from the grade beam or the grade beam cap onto just soil. So we're trying to move the settlement, if you will, away from the abutment, because it's always going to settle to some point. So the first approach span is really just it's a bridge segment, if you will. It's a 20-foot span that just has soil underneath, and then we've got a 30-foot paving section that sets on the abutment or the grade beam cap, if you will, and onto the pavement, or onto the soil.
Okay. What about the piles that hold it up? Are they just the same as your regular piles?
Yeah, so they're typically a little bit less for the way we design it. For this particular project, the abutment pile were 80 feet long. The grade beam pile were 60 feet long. Of course, it depends on spacing and required bearing, but we have made the switch a number of years ago to put all of some people call them a sleeper slab, and they just found it on soil. We actually found it on a deep foundation. We do almost all of our bridges in Nebraska on deep pile foundations. So if the bridge is sitting on piling, the grade beam will also be sitting on pile. So it's just an extension. It's really another span at the end of our bridge.
Okay. Another substructure question. How did the contractor support the abutment precast piece at the specified elevation? Did it just sit on grade?
No, they actually welded onto, they welded a checkerboard, if you will, a form onto the steel pile to hold it up. They didn't feel that the grade was going to support it enough just because it was so heavy. So they welded onto the steel pipe pile themselves.
Okay. And then how did you connect the back wall to the abutment?
Sure. So the back wall, I didn't show that well, but there were some sleeves, just like the sleeves at the piling. There were sleeves that that reinforcing steel from the abutment cap came up. We doweled into the cap. These reinforcing came up, and then we poured some high early strength concrete in those sleeves. We both did it at the abutment cap, and we did it at the grade beam also onto the paving section, onto the section that was further away from the bridge. And I can probably show that right here. So on this left picture, this is the back wall on top of the abutment cap, and so the reinforcing steel that came up through these holes here and then it was poured with high early strength concrete.
Okay. Another substructure question was, any reason sheet piling, and you see it there, was installed behind the abutment rather than in front, so the piles could have been protected against scour?
Yeah, well, so we put them this way. The number one, the bearing pile, the pipe pile, are much longer than the sheet pile. So we don't feel we need to protect the bearing pile. They were 80 feet long. The sheet pile were 33 feet long. And you really need something to hold the top. You know, had we put them in front of the cap, we would have had to somehow attach them. so that so it wasn't just a cantilever. So we considered this, fixed against the abutment top. If we were to do this cast in place, we'd do it similar, but we would cast the sheet pile actually in the abutment cap concrete. So if you can picture that, just like on this picture to the right. So if the soil on the other side were to wash out, at least the top is bearing against this wing, and not, if it were out here, it would more likely just cantilever over, more likely to not support itself.
Okay. We got some questions that came in about the camber and the panels in your superstructure. And it says, why was there only one row of shear studs? And was there any concern about stress concentration and spalling of the haunch?
So this has been something that we've done quite a long time ago. And if Fuad Jabber was here, I would have him answer this question, or Mayor Tadros or George Morcos. So it's I don't have a specific answer for you. I know this has gone through we did quite a bit of research with the single threaded rod stud instead of the dual shear connector. We've also gone through AASHTO T10 and a number of things. So it's I don't have a technical answer for you, besides to say that we've done a lot of research with that, and we found it to work really well. And it was something we've been doing for actually a number of years on accelerated construction. If this were a regular project with the cast in place deck, we would have a normal shear connectors coming out of the concrete girders. And part of one of the last research projects that I showed on the screen is a way to just use a normal shear connector in a concrete girder, and using ultra high performance concrete to connect that to a precast deck panel without having the shear connectors go into the precast deck panel itself.
Okay. There's a question that came in about why such a large width space above the girders and below the deck panels to be filled with SCC, self-consolidating concrete.
Yeah, you can. That's always the argument. We could shorten that up if we wanted to. We feel, number one, with the self-consolidating concrete, it's really not an expensive material. It gives us a little bit more, security, if you will. We talked about if we use ultra high performance concrete for that shim, we would probably move those forms in a bit. But it's for the material that we have, just to make sure it fills in there. We don't feel that with self-consolidating concrete we need to make that more narrow. We don't think we'd save enough money to make it worth the while. For instance, if it were a cast in place deck, we would just use normal deck concrete for that shim concrete.
Okay. There's a question that came in about the camber was mentioned as being 11 inches. How old were the girders when they were placed? How old were they?
I don't specifically know. We have a requirement that they have to be a certain age before they're placed on the bridge itself. The girders were probably one of the first things that the fabricator built, just so they could do their thing with the camber, the initial camber. Yeah, we have I'd have to get that number for you, but we have a requirement that they've got to be a certain age before they can even be placed on the bridge themselves. So they were past that age, but it happens, with the high strength concrete we're using. These were relatively shallow girders. We had quite a few strands inside these girders. We needed to have the shallow girders for the waterway underneath, and it just, camber's hard to predict. Initial camber's a little bit easier, but final camber can be quite a bit different at times. So.
Okay, and then the question was, how was the excessive camber handled with the deck panels?
Sure. So The short answer is we raise the grade. That's about all you can do. You've got to have a minimum. You have to have a minimum shim at the top, at the middle of the girder, and so basically your shims just got larger towards the abutments, and about the only thing you can do is raise your grade to make that work, which is fine, because you extend that out, and eventually you have to taper from wherever your construction ends down to the pavement. And then we also finish things off with a asphalt and membrane, so you're always able to make some adjustments with the asphalt.
Okay. How thick were the deck panels?
They were full depth, but Paul, I don't know off the top of my head. We can get that answer for you, but they were, I would guess they were full depth at 7.5 inches. If Steve Sabra is listening, the designer, he would be able to tell you, but I can get that answer for you.
Okay. A couple questions about the joints that we had. First of all, did the use of epoxy-coated rebar affect your UHPC joints?
I'm going to say no, but I'm going to probably have to lean on somebody else to answer that question. That's from what I know, we were using 6-inch or maybe 7-inch laps with the ultra high performance concrete with the epoxy. So I would have to get back to you on that if we made that lap steel a little bit longer because of epoxy or not. But it was either 6 or 7 inches.
Okay. And what was the curing method used on the UHPC joint?
Typically, well, we had those covers, but then typically I believe they put, you know what, I don't know, Paul. I was going to say we probably put some wet burlap on top, but I don't know that. That stuff cures so fast, and you get such high and quick early strength. I don't know exactly what they did on this project, but I know, as you saw, you had the chimneys and you had the covers, the plywood cover on top. So I know that was there. I don't know if they did some sort of a wet burlap on top of that or not.
Okay. Here's another question on the joints. You had additional surface prep done on the deck panels, and that was where you sandblasted the joints. Was additional surface preparation done on the deck panels, such as rendering the deck panels, the deck joints, SSD, what is saturated surface dry?
Yeah, my answer is maybe. I wasn't there for that part. We'll have to get back to you on that if we required that for the joints. I know of course, you had to prepare by the sandblasting just so the ultra high performance concrete would adhere better. I don't know if we required it to be saturated surface dry or not for the ultra high performance concrete.
Okay. Then the final one on the joints that came in was, you mentioned the joint between the panels and the rail ends was sandblasted, but did any other part of the slab get the same treatment?
So the only thing I believe that we did was where it came in contact with ultra high performance concrete, which were the transverse joints, both on the bridge rail and on the deck panels themselves. I don't believe we did it with the middle joint with the high early strength concrete. I may be mistaken, but I know we for sure do it for the ultra high performance concrete. But
okay,
that's all I know.
That's fine. Let's get a couple cost questions in real quick. Were there any change orders or claims for delay on the project?
Yeah, so we had a couple. I don't know specifically what they were. So we did have some change orders that added some more time to the road closure. The contractor was not charged any liquidated or any disincentive. I'm not sure that they made any incentive either. I don't know for sure, but I know we had some changes that happened that some time was negotiated. So we didn't quite make the 45 days. It was a little bit more than that.
Okay. Do you have any advice on how to make the system cost competitive in addition to being fast?
Yeah, well, do more. You know, that's the one thing our contractors and our fabricators talk about here. You know, this was a one time. Of course, so the cost is going to be higher. I know you're probably going to ask about what the cost was. I don't have those numbers. It was more than we would have paid for a cast in place bridge. But you know, when you do this, especially for the first time, you know, there's some unknown risk that both the fabricator is going to put into their project and the contractor is. Now things went pretty smooth, and I think afterwards, with some of the thoughts that were given out, we always, on projects like this, we always have a physical face-to-face sit-down meeting with not only the suppliers and the fabricators and the contractor and the district folks, just to talk about, okay, how do we get better? So I think with those things, you know, the cost would come down. I would imagine the states that do more ABC see that over time, and I would completely believe that that would happen here. So yeah, it really is just have everybody get more comfortable and mitigate some of the risks that, or maybe even some of the unperceived risk that's out there with these types of projects.
Okay. How has the system performed since it was built in 2018?
You know, it's really doing well. You know, I talked about that a little bit. You know, these precast elements, they're built in a controlled environment. So the precast elements themselves are going to be really high quality. And the biggest thing with any of these types of structures is the connections. If you can get good connections that last, you know, this bridge is going to last a long, long time. So, and we feel that we took extra care when we did the connections, both the high early strength concrete and the self-consolidating, and of course the ultra high performance concrete. But I was out there in the spring, and it just, you know, it looks as good as the day we built it. Of course, it's just, you know, 3 years old, so we've got about 97 years to go. But yeah, it's really holding up well. We're really happy with it. You know, we did put a waterproof membrane and asphalt on the deck, so I think that's going to help us. But boy, when you've got a pre-stressed deck, that thing's just going to last a long, long time. As long as all the connections hold up, we're going to be fine, and we really think we've got good connections on this project.
Okay, one more question, and then I'm going to turn it over to Romeo. People wrote in and said, we fabricate forms. Do you have any comments on what you, the contractor, or the fabricator, would like to see in forms?
You know, that's a fabricator question. You know, this was our first one like this. I think if we would do more, we'd definitely want to do more standard type details, or standard, you know, wings or abutments or whatever. And then we could, you know, do some more of a permanent type form. As you saw if you saw on the fabrication photos, most of these were just handmade forms to make things, you know, they put them on their beds for their other type forms. So I don't think anything was a long-term, you know, use again over type form, except the girders. You know, of course, we've been using these end-use girders for a long, long time. So they've got, you know, good forms for those. But the other ones were all just kind of one-offs for now. But if we start doing this more, I can see that would need, the fabricators would definitely need some good quality forms.
Okay, Romeo?
Yes, thank you, Paul, and very good questions. I have a couple of design related questions that I'd like to add. So are the abutments integral? If so, what details did you use to connect the girders to the abutment diaphragm?
So the abutments are semi-integral. So yeah, so this picture right here, I mean, these sheets would be driven down further, of course, but and these sleeves would be filled, but then there'd be basically a bond breaker on top of the back wall. And so the girders are on a sole plate. So the girders, the deck's on top of the girder, the precast deck is attached to the precast approach slab. I'll show you another picture of that down the way here. So right here, you can see where the precast deck is attached to the precast approach slab, and there's basically a bond breaker on top of the back wall. So they're able to move over the back wall and all the expansion is taken up on the grade beam on this left picture, which would be out here. So they're semi-integral.
Okay, thank you, Mark. And just one final question. Design-wise, was the deck and girders considered fully composite?
Yes. Oh, for sure. Yeah. For sure. That's why we had the research on those shear connectors, why we do the self-consolidating concrete, why we do the pockets, why we do all that. So yes, for sure they are.
Thank you. And that's all the time we have for questions. I'll turn it back over to Ettore.
All right, Mark, stay on with us just for a couple of more minutes. So thanks for the great presentation. Like I said, I mean, always when you look for new ideas in the bridge engineering, look to Nebraska. That's where ideas come from. So thanks for the great presentation. Thanks to Mary Lou, Paul Lodz, Romeo to moderate the question and answer period. Again, Mark, thanks for the excellent presentation. So on that note, we will conclude our webinar today, and we look forward to have you for our next webinar. Okay, so long.